We'll learn the topic linear algebra. Linear algebra. Linear algebra is an important basic topic of mathematics. It is also an important tool in engineering and sciences. It has lots of application in almost all areas of engineering and also science disciplines. The topic linear algebra is based on an important algebraic structure that is called vector space or linear space. Again, in a vector space, we deal with two type of elements, that is vectors and scalars. So, first let us know what are scalars. To know scalars, we have to recall two important basic algebraic structures called groups and fields. So, we will start with this groups. This is a very basic topic in abstract algebra. So, a group G is a non-empty set together with non-empty set together with a binary operation star. This may be represented as a pair G star. And is satisfying the following conditions. First one is that is called closure property. For any two elements A and B in G, A star B belongs to G. This is called closure property. This is called closure property. For any three elements A, B, C in G, A star B star C is equal to A star B star C. This is called associative. And third property is this: there exists an element E in G such that A star E is equal to E star A is equal to A for all A in G. This element E is also called identity element. E is called identity element. Of G. And fourth property is this: for every element A in G, there exists B in G such that A star B is equal to B star A is equal to E. here A and B are called inverse of each other. Again, we say that a group G is commutative if for every element A and B in G, A star B is equal to B star A. Next, let us see some examples. Some examples of groups. First one is that very natural one, that set of all real numbers with usual addition operation is a commutative group. Similarly, we can also see that set of all integers with addition operation is a commutative group. However, if we see the set of all natural numbers with respect to addition is not a group, where n is the set of all natural numbers, where n is the set of all natural numbers. So, next we shall see the definition of a field, which is very much useful in vector space. In defining a vector space, we need this algebraic structure that is called a field. A field F is a non-empty set together with two binary operations, plus and dot. This may be represented as a triplet F plus dot and is satisfying the following conditions or following axioms. First one is F plus is a commutative group and second condition is F minus 0 with respect to this dot operation is a commutative group. Where this 0 is the additive identity of F, that is identity element of this group F plus. And third condition is also called compatibility condition. In any structure, whenever we are having more than one operations, we should have this compatibility property, and this is also called distributive property. For any three elements A, B, C in F, A dot B plus C is equal to A dot B plus A dot C. In other words, this dot operation is distributive over addition. This is called distributive law. So, here for some terminologies or some definitions that we refer and again that we will give as a remark sort of thing, that in a field, first remark is this: in a field F plus dot, this plus is called addition and dot is called multiplication. Of course, they are not necessarily the addition and multiplication operation on the set of real numbers. These plus and dot symbols, they just represent two binary operations, and their names have been given as addition and multiplication. There need not be usual addition and multiplication operations on set of real numbers. They may be any binary operation. So, that we will see example later. Here this 0 is called, or this the identity element of A plus is called the additive identity, and denoted by 0. The identity element of F minus 0 dot is called the multiplicative identity, and is denoted by 1. Okay, this is then fourth remark is like this: it is known that identity element of a group is unique. So, 0 and 1 are also unique. So, fifth observation is like this: it is also known that inverse of an element in a group is unique. Therefore, for any element A in F, the additive inverse the additive inverse of A is denoted by minus A. Next, we shall see some examples of fields. So, again we are having this very natural example is this set of all real numbers with usual addition and multiplication. This is a field. And second one also we are having this set of all complex numbers with respect to addition and multiplication. This is also a field. We will see another example that set of all integers with respect to addition and multiplication. This is not a field, because we will not get multiplicative inverse of elements in Z. So, fourth example is we will see an example of a finite field. Here all the examples we have given are examples of infinite field. So, let us see one example of a finite field. So, for any prime P, ZP is a field where ZP is the set of integers modulo P, that is, in other words, ZP is the set of remainders of integers when divided by P. Of course, the operations on ZP with respect to which ZP is a field are addition modulo P or addition modulo P and multiplication modulo P. For example, consider Z5. So, Z5 will be So Z5 will be the set of remainders 0, 1, 2, 3, 4. Here on Z5 we will have this addition modulo 5 operation is like this: 3 plus 4, that is equal to 2 modulo 5, and 3 into 2, that is equal to 1 modulo 5. So now these fields, here we can have this note that the field are the fields R plus dot and C plus dot are called real fields and complex fields respectively. Complex field respectively. So now we are ready to give definition of a vector space, but before that we like to recall another important objects that we need in this linear algebra are matrices. Matrices play an important role in linear algebra to represent various concepts. So let us see matrices. So as you know, this matrix, a matrix of size, a matrix A of size m by n, denoted by Aij m by n, is a rectangular array of m rows and n columns, and is enclosed with brackets. Here this matrices, here these entries, here the entries Aij, entries Aij of A may come from a field F, and in this case A is called a matrix over F. If m is equal to n, then A is called a square matrix. Is called a square matrix. For a square matrix, Aij n cross n, the entries A11, A22, ANN is the entries is called the main diagonal or main or principal diagonal. Again, if all the entries of A, if all the entries of A are equal to 0, this 0 is 0 of the field, of course, of the field, then A is called a 0 matrix, and sometime we denote by 0 also, and is sometime denoted by 0. Here we will have also diagonal matrices that we will see. So, we can have this diagonal matrix. A square matrix A is called a diagonal matrix if all the off diagonal entries are 0, diagonal entries are 0, 0, that is, if the entries of A are Aij, then Aij equal to 0 for I not equal to j. So, now we can also say that true matrices are equal, that equality of matrices, two matrices A and B are said to be equal, two matrices of same size, that m by n and B is also a matrix of size m by n, are called equal if Aij equal to Bij for all I and j. So, now we can have algebra of matrices, that we can add two matrices, we can subtract two matrices, we can have scalar multiplication of matrices, and also we have product of matrices or multiplication of matrices. So, now we can say this algebra of matrices. So, first we shall see addition of matrices, that suppose we are having two matrices A and B of same size, A be a matrix of size m by n and B be a matrix of same size m by n over the same field F. Then addition of A and B then addition of A and B denoted by A plus B is the matrix C whose entries are Cij, where Cij is equal to Aij plus Bij for all I and j. We can also have scalar multiplication of matrices, that we can have also this scalar multiplication of matrices that is for any matrix A with entries Aij of size m by n over a field F and any element alpha in F, alpha A is the matrix with entries alpha Aij, that is alpha A is equal to alpha Aij of size m by n and is called a scalar multiple of A. So, next we will have some properties of addition and scalar multiplication, which are very useful, that we will have some properties of addition and scalar multiplication of matrices. Scalar multiplication of matrices, that first property is A plus B is equal to B plus A, that is commutative. Matrix addition is commutative. Here A and B are any matrices over same field and same size, are matrices over F and are of same size. We will also have that A plus B plus C is equal to A plus B plus C, that is associative property. Here also matrices ABC are over the same field F and same size. A, B, C are matrices over F and are of same size. So, here if we add the 0 matrix, that A plus 0 is equal to A for every matrix A. Of course, the size of this matrix A and size of this matrix 0 are same, where A and 0 are of same size. So, fourth property is that we can also have this negative of a matrix, that A plus minus A, that is equal to 0. So, where A is Aij implies minus A is equal to minus Aij. So, next we will have some properties of scalar multiplication, that is fifth property. For scalars alpha and beta in the field, elements of this field F are of course called scalars. For alpha beta belongs to F and matrix A over F alpha plus beta times A is equal to alpha A plus beta A, and here for alpha in F and matrices A and B over F of same size, alpha into A plus B is equal to alpha A plus alpha B, or in other words this scalar multiplication is distributive over matrix addition. Also we are having this for scalars alpha beta in F and matrix A over F alpha times this beta A, this is equal to alpha beta A. So, next we will see a multiplication of two matrices, or also called product of matrices. So, that is called matrix multiplication or product of two matrices. So, it is defined like this: if A be a matrix of size m by n and B is a matrix with entries b I j and size n cross p, n by p, are matrices over a field F, then their multiplication or product is the matrix C with entries C I j, and this will be of size m by p, and these entries are given by C I j is equal to sum of A I k, B k j, and k runs from 1 to n. Next, we will see some properties of matrix multiplication. Properties of matrix multiplication. So, one important property of matrix multiplication is that this need not be commutative, that matrix multiplication need not be commutative, that is, there exist matrices A and B such that AB is not equal to BA. However, this matrix multiplication is associative, that for matrices A with entries A I j, that is m of size m by n, B is a matrix with size n by p, and C is a matrix of size p by q. Then we have this A into B into C is equal to A into B into C, that is associative. Also, this matrix multiplication is distributive over addition. For matrices of suitable sizes, that we have A dot B plus C, that is equal to A dot B plus A dot C, that is left distributive. This property is called left distributive. Similarly, we have that right distributive property that also holds for this matrix multiplication. So, that is for suitable matrices, for matrices of suitable sizes, this A plus B dot C, that is equal to, A, that is equal to that AC plus BC. This is called right distributive. Right distributive. Then we are having some special matrices. Before that, we see this transpose of a matrix, transpose of a matrix. This is very useful throughout this linear algebra. So, if we are having a matrix A with entries Aij and size m by n be a matrix over F, the transpose of A we denote like this, denoted by A transpose is the matrix A transpose is equal to Aj, that is of size n by m, or in other words we get transpose of A by writing the rows of A as columns of A transpose in order. So, we can have this properties of transpose, properties of transpose of a matrix. So, first property is like this: for any matrix A, if we take its double transpose, transpose of A transpose, that we get the same matrix back, that is equal to A. Second property is for matrices A and B over F and of same size, we have this transpose of A plus B, that is equal to transpose of A plus transpose of B. So, another property we will have is this. So, if A and B are for matrices A and B over F of sizes m by n and n by p respectively, that transpose of product of A and B, this is equal to product of transpose of B and transpose of A. So, it will be reverse, the product will be in reverse order. So, then next we shall see some special matrices, some special matrices. That first one is this symmetric matrices. They are also very important type of matrices. So, a matrix A, basically this is a square matrix of size n by n, is called symmetric is called symmetric if A transpose is equal to A, or in other words, that entries of this, that is Aij is equal to Aji for all I and j. Here the entry is can be element of any field, of course. Here Aij can be elements of any field. Of course, some people they consider elements of a symmetric matrix are real numbers, but in general we can consider the elements be elements of any arbitrary field. Then we say that a matrix A is skew symmetric, that is skew symmetric matrices. A matrix A with entries Aij, this is also square matrix, is called skew symmetric if A transpose is equal to minus A, that is it satisfies this condition that Aij is equal to minus Aji for all I and j. So, another important kind of matrices are Hermitian matrices, and they are defined over complex fields only. So, let A be a square matrix over complex field over C, then A is called Hermitian. A is called Hermitian if A conjugate transpose is equal to A, that is where this A conjugate is equal to Aij bar, that is the complex conjugate Aij bar are the complex conjugates of Aij. Here also we define this skew Hermitian matrices, So, we say again a complex matrix A with entries Aij, of course, this is square matrix, is called skew Hermitian. Skew Hermitian if A conjugate transpose is equal to minus A. So, quickly we can have some properties of these matrices, that properties of spatial matrices, that first property is that symmetric matrices and Hermitian matrices agree on the real field. Second property is that for Hermitian matrices, all diagonal entries are real. All diagonal entries are real, and for skew Hermitian matrices, diagonal entries are either 0 or pure imaginary. So, next we will also discuss.